Hello everyone, my name is Rina Chow and I am a bioinformatician at the Monty Lab under the supervision of Professor Stefano Monti at the Boston University. Today I will talk about CaDrA, a containerized and cloud-deployable open source software package for candidate driver analysis of multi-omics data. So CaDrA is short for candidate driver analysis. It is a statistical framework that we developed to support the identification of genetic and possibly epigenetic drivers of molecular phenotypes of interest. Here is an overview of CaDrA workflow. Basically, CaDrA takes two inputs. The first one is a binary multi-omics dataset, where the rows are 1 or 0 vector, indicating the presence or absence of omics features, just as mutation, copy number alteration, epigenetic mark, etc. The second one is the molecular phenotypes of interest, represented as a vector of continuous score. This sample-specific score can represent a phenotypic readout of interest, just as protein expression, pathway activity, drug sensitivity, etc. First, CaDrA chooses a starting features, which either a single feature having the best score based on a given scoring function, or a user-specific starting features. In the next step, the union or logical OR of these features, which each of the remaining features in the dataset is taken, yielding a meta feature with its corresponding score. If any meta feature has a better score than the hit from the previous step, the new meta features is chosen for the next iteration. Repeat step 2 and 3 until no further improvement in score can be obtained. The final output yields a set of features known as the meta features whose union have a local maximum score and is permutation-based p-value. Here we will illustrate the usage of CaDrA by walking you through its application to one of the datasets provided with the package. In particular, we are using a dataset of semantic mutation and copy number alteration extracted from a TCGA breast cancer dataset. This is known as the feature set. We query this feature set based on an input score that measures the per sample activity of YAG tag, the two important regulator of Hippo pathway. This score represents the projection on the TCGA breast cancer dataset of gene expression signature of YAG tag knockdown derived in the breast cancer cell lines. And here we are asking the question, what is the combination of genetic features, just as mutation and copy number alteration, that best explain or predict YAG tag activity? The results returned by the application of CaDrA are summarized in this plot, which is actually one of the package output. The top panel shows the input score sorted from largest to smallest, measuring the YAG tag activity. The mid panel shows the three genetic features, 2 copy number losses and 1 mutation as black ticks, and the union meta feature as red ticks. Finally, we use a KS-based scoring function to carry this dataset. The bottom panel shows the mountain plot of the enrichment score corresponding to the red meta features. In other words, CaDrA finds the combination of 2 deletion and 1 mutation to be the best predictor of YAG tag activity in BRCA dataset, which suggests they may be important driver of this molecular phenotype. There are 2 versions of CaDrA. In the first implementation of CaDrA only supports rank-based scoring function based on Kuno-Muro Slipknot test or Wisconsin test. It was only available as a type of script, downloadable from GitHub with minimal documentation, no QAM or bioconductor compliance structure. And the dependency have to be independently resolved and installed before one can install and use the package. And so we developed a new version of CaDrA, CaDrA 2. It is now implemented as a bioconductor compliant package with thorough documentation, including vignette and tutorial that utilize the sample dataset included in the package. CaDrA 2 incorporates additional scoring function not available in the original package. These include mutual information as implemented in the Revealer package and the specification of custom, a user-provided scoring function. The code base of CaDrA are clean, hardened, and optimized as an open source R package developed based on best software engineering practice and design principle. It is now meet bioconductor and diverse style guidelines. We use R-based profiling tools and packages like microbenchmark and ProViz to identify and remove potential bottleneck in the code to ensure efficient performance of the package and its scalability. We designed and implemented unit tests for all functions. We also implemented a Shiny R interface that supports multiple query modalities and multiple visualization options. And we defined Shiny modules to support the integration of CaDrA into other applications. Finally, and more importantly, we containerized the package and all its dependency as a Docker image, available through Docker Hub, ready for cloud deployment. The analysis of CaDrA can be complex and memory intensive, especially when it's come to perform permutation-based testing with hundreds or thousands of iterations. Therefore, it is quite difficult to run CaDrA on a personal computer, as it often lacks the memory and computing power to run just an expensive task. This is why we currently rely on Node, a cloud computing service that is available to many institutions in New England, to help us allocating resources needed to improve CaDrA performance and its scalability. It is easy to create a project and launch a CaDrA instance on Node VM, as it is already containerized and cloud ready. Additional resources can be requested and allocated to CaDrA project to boost its computing power and increase its memory capacity. Node also have a public-facing service where we host the Shiny interface of CaDrA. Overall, Node have helped us share and distribute the analysis of CaDrA to a wider research community. You can access the code base of CaDrA on our GitHub repo, which include extensive documentation and tutorial on how to use the package. We're also finalizing our submission of the package to Bioconductor. We containerize all of the dependency needed to run CaDrA using Docker. The containerized Docker image of CaDrA is now available on our Docker Hub. Researchers can easily pull this image and reproduce our work on any machine that runs Docker. We also successfully tested the deployment of our Shiny interface on Node VM using our containerized Docker image as well. The package can also be deployed on AWS and Google Cloud. Please check out our provided link for more detail. In summary, CaDrA is a statistical framework that we developed to support the identification of genetic and possibly epigenetic driver of a molecular phenotype of interest. CaDrA was developed as a bioconductor package with thorough documentation, vignettes, and unit tests. The key features of CaDrA include multiple scoring functions, optimized core function in C, or Shiny interface, and Docker containerization. The analysis of CaDrA can be complex and memory intensive, and thus Node has become an important cloud computing service that we rely on to allocate resources needed to boost its performance and scalability. Lastly, Node has a public IP service that we currently use to host our Shiny application of CaDrA. This service allows us to share and distribute the analysis of CaDrA to a wider research community. For more information about this project and other research led by Professor Stefano Monti, please visit the Monti Lab page for more detail. Last but not least, we would like to say thank you for NICDR who funding make this project possible. This is all for my presentation. Thank you.